We are now going to relate simple harmonic motion to a circle, to an object moving in a circle. And in the end, we'll come up with a formula for the velocity at any position along the axis. Now we're going to consider this here being the x-axis. And this is the path of the object in uniform circular motion. So it's an object moving in a circle at a constant rate. We could think of this as looking from above. This is a top view. And so we can see we have privy to the x-axis and the y-axis. And there they are. And so we can visualize that all great and well. But what I want you to be able to visualize now is projecting this motion into one dimension. This is two-dimensional motion. We're going to project that motion just onto the x-axis. So you could think of it as shining a flashlight from above, for instance, on this object and see its shadow projected onto this axis. Or just put your eyeball up here or put your eyeball underneath here, looking this way, and all you're going to see is the back and forth motion of the object, not the motion that's away and toward you. Does that make sense? I hope so. So we will look at this in one dimension, project it onto one dimension, that is the two-dimensional circular motion. Well, let's give that a shot. So here we have on the x-axis, all right, x is equal to 0 here, and it can go between these limits. As the object rotates around here, then it's moving from here over to here, all the way back again, etc. Back and forth along here in SHM. That's what it's doing. Okay, so over here is x max, and x max is the amplitude. The amplitude. So I'm going to draw a radius, and the radius is the value of x max. Here's the biggest x can get. All right, so that is equivalent to the radius of the circle. So the radius is the maximum x. Now where it is right now, I'm going to assume that you're looking from the bottom here, underneath, and you're seeing this object here, but projected onto the x-axis, it's right here. So this is where you're seeing the object. So it's at a particular position in the x. We're just going to call it x. And there's some angle theta here, some angle theta between the x-axis and the position on the circle itself. You don't see the circle. You don't see it from below or above. But you do see where the x position is. But we now know that there really is an angle here between the x-axis and where it is on the actual circle. Okay, moving on to the next idea. The object is moving and it's tangent to the circle. The motion is always tangent to a circle. So this is the circular motion speed or velocity, okay? Centripetal velocity. And that's the maximum it can ever be in the x direction. The speed as indicated here is the biggest that ever appears when looking under here or above, all right? And so since we're just looking at the x-axis part of this, it's only part of that velocity is projected in the x, and it's this part. There it is. That is Vx. Now, this angle and this angle are the same. You see these two angles here? They are perpendicular to each other, and this is perpendicular to this. And so this side and this side are connected as well. Well, in any case, this angle, from what I just said, and this angle are the same. So hopefully you can be convinced of that. And now, the question I have is, where is the object moving in uniform circular motion when its x-axis velocity? This is the maximum it ever gets, Vmax, which is also the circular motion velocity. So where in this circle, looking from above or below, is this going to be the same value as the circular motion velocity? Well, hopefully that makes sense, and you have an answer for that. Isn't it going to be when it's right here, when this is all projected horizontally of the same length? So the location is the top or bottom of the circle. And the value of x there is, well, what is the value of x here? It's 0, that's right. Okay. Now what's the formula for circular speed or centripetal velocity? What is the formula, the basic formula? For an object in uniform circular motion, the speed is 2 pi r over t. What's the value of this maximum x-axis velocity vx? Well, by analogy, vx max is that speed, and so it's 2 pi x max, the x when it's at that max speed, okay, over t. That's the same thing, which is the amplitude. So it's 2 pi a over t. That's the maximum x velocity. And that maximum x is the radius or amplitude, just to repeat myself. Now, the position and velocity triangles. What can you say about this triangle and this triangle? That's right, they are similar. So you can use Pythagorean theorem to, first of all, it's a 90-degree angle. So you can determine what the value of this is over here, the side opposite theta, and relate these two together. So let's do that. This is square root of r squared minus x squared. That's the value of this. For simple harmonic motion, what does r represent? The radius, well, it's the value over here, which is the amplitude. Now, let's compare these similar triangles. So I'm going to look at the ratio. Vx right here over V max, the ratio of that is the same as the ratio of this and this, these two, okay? So Vx over Vx max is square root of r squared minus x squared over x max. And you know what x max is? It's a. And so is r. r is equal to a. So we have square root of a squared minus x squared over a, the amplitude. And so we can solve for Vx. Vx max times square root of a squared minus x squared over a. But now Vx max, or V max, same thing, is this. So let's go ahead and include that idea. Vmax is Vc is 2 pi a over t. So now Vx equals 2 pi a over t, square root of a squared minus x squared over a, and a's go away. And there's our formula for the speed of an object in uniform circular motion anywhere on the x-axis. This is the formula for the speed. This 2 pi over period, square root of the amplitude squared minus its position squared. Notice x could be in the plus or in the minus direction. It doesn't matter because it's squared. But the biggest that this can be is where you get rid of x. In other words, x is 0. And so the square root of a squared is just a. So it's just 2 pi a over t, which is the circular motion speed. So it all comes together. In fact, what happens when it's moving, when it's not moving at all? It's not moving at all at the very ends, where x is equal to a. A squared minus a squared is 0. Indeed, it works. So there's a nifty formula for determining the speed of an object in uniform circular motion. I hope you enjoyed that little exercise and derivation.